Hello everyone, I will talk today about Axion Quasiparticles for Axion dark matter detection. My name is Schütte-Engel and this work was done in collaboration with David Marsh, Alexander Miller and others. And it is based on two publications, one PRL from 2019 and one more recent paper which has been recently accepted by JCAP. So I will focus in this talk on the second paper where we carefully work out the theoretical foundations for this approach to detect Axion dark matter. This talk has three parts. In the first part, I will motivate what we are doing. In the second part, I will tell you something about Axion Quasiparticles, which I will also sometimes refer to as condensed matter axions, because these are quasiparticles in condensed matter systems. And in the third part of this talk, I will tell you how these Axion Quasiparticles can help us with the detection of particle physics axions, which can be also dark matter. Alright, so let's start with the motivational slide. So I'm showing the dark matter axion, the particle physics axion mass against the axion photon coupling. The colored transparent regions here are future sensitivity curves of future experiments, and the non-transparent curves are already ruled out. It is quite clear from this case that there are no Axion haloscopes which are actually sensitive to Axion dark matter in the milli-electron volt regime, so around here, and which are also sensitive to the QCD Axion band. And in this talk I will tell you how one can use Axion Quasiparticles to detect Axion dark matter in this interesting milli-electron volt range. Okay, before I do that, I have to tell you what are Axion Quasiparticles. So Axion Quasiparticles can be established in antiferromagnets. And in antiferromagnets you can have longitudinal and transverse spin waves, and very basically the Axion Quasiparticle is the longitudinal spin wave. So consider, for example, here an antiferromagnet where the spins are pointing upwards, and in this lattice the spins are pointing downwards, and then you apply an external B field. And when you do that, the spins are processing on this circle here. And the longitudinal spin waves is actually a variation in the z component of the spin vectors. And there can be spin waves, which are depicted here as this yellow, with this yellow line. So the antiferromagnet is described by a Neal vector, which is the spins on lattice A, upper lattice, minus the spins on the lower lattice. And the Axion Quasiparticle is now the z component of the Neal vector. And it was shown in 2010 that this delta theta couples to E dot B as axions in in particle physics do. There are several proposed material candidates. However, let me stress that it was not experimentally proven until now that these Axion Quasiparticles exist. But it's a very active field of research, and two proposed material candidates are here. And it's very hard to grow these materials in the lab. However, for this kind of material, there's a claim that it was successfully grown in the lab quite recently. So in the second part of this talk, I will theoretically describe how one could in the future take these materials and check if there's really an Axion Quasiparticle inside. So detecting Axion Quasiparticles, that's the next slide. So the key of this is the dispersion relation. So inside these materials you have the mixing of the Axion Quasiparticles and the photons, and you end up with an Axion polariton, which is the mixed state, so to speak. And the dispersion relation for the Axion polariton is actually k squared times an effective refractive index squared times omega squared, and the effective refractive index squared depends on the refractive index times a parameter b, and this parameter b is proportional to the external B field and some material parameters, and it also depends on the Axion Quasiparticle mass. The Axion Quasiparticle mass, we're always setting this to 2 MeV, and this is a theoretical prediction until now. This 2 MeV always tells you that we are already at the right scale. So in the end we want to have Axion dark matter detection in the MeV range. So if the Axion Quasiparticle mass is in the MeV range, so this sets the right scale. And we also define this omega LO, which is the squared sum of m theta squared plus b squared. So this function is plotted in this figure, and it's quite clear between the axion quasiparticle mass and omega LO there's a gap, and inside the gap the dispersion relation is purely imaginary. So this means that inside the gap there are no modes of propagation, and this is the key to detect the axion quasiparticles. Consider you have a sample where you think that there are axion quasiparticles inside, and then you shine with a terahertz laser onto the sample. And when you're really inside the gap, if the laser frequency is inside the gap, there are no modes of propagation, so everything should be reflected. These experiments are done at the moment by Caterina Braggio in Italy, and we are all very excited what comes out of these experiments. Let me show you what we theoretically think should come out. So we have done the signal calculation in our paper, and here are actually the results. So here's the frequency of the laser which shines on the sample, and here's the transmission coefficient. And in different colors I'm showing different predictions for the transmission spectra for different external B fields. And what we also show is the case if there's no axion quasiparticle inside, then you should just get the transmission spectra with the dashed line. So yeah, here. And the first message is that it's very clear how one can distinguish these two cases, if there's an axion quasiparticle or if there's no axion quasiparticle. The second important message here is that if you have in the future some measurements, you could fit these measurements to our predictions and then determine all the material parameters of your axion quasiparticle material. For example, we have included also losses here in this calculation, gamma m and gamma rho, magnon and photon losses, and you could basically fit these parameters by fitting these to our theoretical model. So this will be quite important in the end, because when we want to do a dark matter axion search with these materials, we need to know all the parameters of these axion quasiparticle materials. Okay, so in the third part of this talk, I will now assume that these axion quasiparticle materials have been established, that we have them. So what can we do with them? How can we search with them for axion dark matter? So the principle is here. There are axion dark matter in blue, they are coming in. And inside the sample, we have axion quasiparticles, axion dark matter, and photons. And there's a resonant mixing between these three ingredients. And then the outgoing photons are resonantly enhanced, and they hit a detector, a single photon detector. So this is the concept behind TURAT, the topological resonant axion detection. Okay, so how one can actually do the signal calculations for the photons? One has to solve the Maxwell-axion equations now with an axion quasiparticle, delta theta, and the dark matter axion A. And you need two Klein-Gordon equations for both axions. So we have done this calculation in our paper, but I will not go through this calculation here. Instead, I will tell you in a very pictorial way how one can imagine this resonance which is going on inside the material. So for this, consider the effective refractive index with respect to omega, and consider we are at the right-hand side of this omega LO, but we are very close. So the refractive index, which goes to 0 here, actually can be much smaller than 1. Okay, now assume that we are at this frequency, and in this case, I'm making the example here that the effective refractive index is 1/2. The axion-induced field, which is shown here in blue, is enhanced in the sample, and outside of the sample is just 1 in vacuum. Okay, but this cannot be, because the electric E field over the interface has to be continuous. So to get it continuous, you have to add some propagating modes. So for example, if you add the propagating mode on this side, you have 1 from the blue, 1 from the red, you end up at total field at 2. Here the total field is 4 minus 2, it's 2, so you have a continuous field over the interface. And this mode is propagating to the left, and this mode is propagating to the right. You can do this for both interfaces. And then you consider the radiation which is coming from the left side and is hitting the interface on the right-hand side. So what you have to do now is you have to apply some transmission and refraction coefficients. So this amplitude multiplied by this transmission coefficient yields this dotted curve here, and this amplitude multiplied by this reflection coefficient gives this propagating mode here. And you add this propagating mode to this propagating mode because they are in phase, and then you end up with a larger amplitude, and you add this to this, and then you get a larger amplitude. So you do this recursively, you propagate the fields between both of these interfaces back and forth, and in the end you obtain a total field which is very much enhanced. And the enhancement factor is called the boost factor, and this is proportionate to 1 over the effective refractive index squared. Okay, so from this picture you can easily read off the resonance conditions. So there's a half a wavelength inside your sample. That's why the phase depth n theta times omega resonance times d should equal to pi. And the effective refractive index, just as a reminder, is given by this formula. And in this formula, the parameter b can be tuned because it's proportional to the external B field. This means you can easily tune the resonance by tuning the external B field and scan different axion dark matter masses. Okay, so as I said before, we have also calculated this, and they are also in our paper analytical formulas for this enhancement factor. So this is written down here and plotted up here. So here we can see actually how the boost factor looks in the vicinity of this omega LO. And as we expect, it's very much enhanced close to omega LO, where the effective refractive index is smaller than 1. And this picture was shown for a fixed thickness of 2 millimeters and an fixed external B field. If you would change the external B field here, we would move the resonance frequency to another axion dark matter mass. Okay, so right now I have not discussed different losses, so I was always in the lossless limit. However, the materials have losses. And what we can do actually, so we can, for different thicknesses, we plot the maximum boost factor for different losses. So consider, for example, the loss of 10 to the minus 4. And in this case, we see that the optimal thickness is around here. So the bands, they depict a varying refractive index. Yeah, so the optimal thickness also depends on the refractive index. But the main point here is that there is an optimal thickness, and we can even write down an analytical formula for this optimal thickness. If you're interested in the derivation of this, you can have a look at our paper. Okay, so to compute our sensitivity range, we assume an external B field which is varied from 1 Tesla corresponding to the lower mass range to 10 Tesla corresponding to the higher mass range. And we assume a total scan rate of 3 years, and we have one sample of this Axion quasiparticle material, and we fix the thickness of this sample to the optimal thickness which corresponds to the middle of this regime, because we cannot change the samples all the time. Okay, so these are the sensitivity reaches for 2 different materials, and we also vary different single photon detection efficiencies and dark count rates. And here are losses which are also varied. In the best case, we can probe a large part of the QCD band, and we are exactly sensitive, which I promised you at the beginning, in the theoretically very well motivated milli-electron volt range. The only competitor so far in this range is IAXO. However, IAXO is quite complementary to what we are doing, because if IAXO will detect a signal, it is completely unknown at what mass the axion will be. So in our case, we scan the range, and when we find a signal, we will explicitly know the mass of the dark matter axion. So let me conclude. So Axion quasiparticles are expected in condensed matter systems, and they can be very helpful to detect axion dark matter in the milli-electron volt range. Okay, thank you for your attention.